Yeah, hi. That's good evening, everyone. And that my name is MD Raza. Just 1 minute. And I am PMRF scholar in the Department of Mechanical Engineering at Trichapalli. And I am the TA for this session for the course of that is machine learning for engineering and science application. And so far we have done with 2 week, and that we are is still in the starting phase. And we are going through the basics that what we need for our machine learning, or it's going for the core of the machine learning courses and all. Because the first that week we have seen like algebra, that how it's going to useful and all, because that it's going to involve full of algebra, and along with that probability, like it's a uncertainty will be there, because we have to do anyhow in the last or at the end, we have to do some sort of predictions or classification. That's all depends upon the probability itself. So that's a very important to we should have the idea that how we have to proceed with that and all. So first lecture we have seen that first week that we have seen like how the probability that matrices, and then how we can go for that scalar or vector and all, and we have proceeded further and all. Once we have finished with that, we have introduced something called expectation, like a probability, and we didn't went for the statistic and all. I think that we that is another foundation or another that is going to basic fundamental code that's required for the machine learning and all. So hopefully that you'll be all aware of that. And one more thing, that for this course, the request it was like to have some basic programming, that the requirement that we all know that like either in the case of Python, if you have that went through this week lecture, so there is a one lecture was there, that is an introduction to package, like that's what deal with Python, then the MATLAB in the Python, and other that open source software was there, that is TensorFlow and the Google Colab and all. In that, like we because that we all know that when we are going to deal with the when we have single variable, double variable, that we can deal with the hands or even with the traditional methods and all. But once that there will be a multi-variable, or maybe the multi-class classifications will be there, so that we have to be very careful, or it will become a bit of complicated to solve with the hands and all. Okay, so it will be like this only, so that we have to aware of that how it will go and all. So that we have to see around. So at this for this course, that there is MATLAB have been given that access, even for that the support for the MATLAB also given. So I will suggest you to take the use of it if you are not like that starting point of that to going into the machine learning field and all. If those who are into the that one programming and all, so that will be good enough, that if you are, or whatever your that is the programming, that is skills that you have, you can go proceed with that also. But as we all know that for the support for the MATLAB will be provided from the that MATLAB team, like that is also limited support, but not the fully support will be there. And for other platforms, might be that we can deal with the concept and all, but the programming part that you have to deal with by your own. So still, and like we are in the third week of the lecture, and the third week we are going to see the optimization problems and all, like optimization, that how it going to, because if you see that the machine learning, that main agenda is to what is to like that we have to map the input to the output. Either that input is there and output is there. Now we have to train it, validate it, and then we have to map it. So that's how it things, or it's something that we are going to learn from the experience or maybe the mistakes. Like if it's the case of that's going to be like that is RL, or maybe that, or either the things are coming with the that auto encoders and all will be there. So that the whole agenda, so that we have to get the best optimum parameter, like at what point we'll get to that our that maximum point, or maybe the validation where the error will be less, where that our classification accuracy should be high, or maybe the uncertainty, if we talk about that variability should be less, or maybe the entropy should be less, and so that is the how and stability should be high. So this is the all things that still this week also we are not going to start the main core of machine learning courses and all. That will today we'll discuss more of what we can say. that is the optimization and all. So can anyone tell, like, before jumping to the optimization, like that the machines, how they're going to store the number? Can anyone tell, like, how it's going to store the number and all? Because if we see in the maths or pen and paper, that we can like float or we can plot the numbers like anything. But the machines, how it going to store it in all? Can anyone tell? We can have the interactive session. If you have some doubt, you can ask, and then formally, like slowly, we'll proceed ahead, or like we'll go ahead with the content for this week. If I'll show you the agenda of this week, that how it will go. Is it third week we are? So that the machine representation of the numbers, and then what we have that overflow, underflow conditions, numbers, and all that will be there. Then it will follow with the derivatives, scalar. Then gradient will be there for the vector. Hessian again with the for the vectors only with the two or three types like will be there. Then we'll go with the metric calculus will be there. That Taylor series will be there. Lagrange equations will be there. Then we have the optimizations will be there. Optimizations like it's a unconstant. Like we have to find out like best optimum value or either the maximum, either the minimum, either the saddle point. When we don't have the in range, in the full range, we can find out. Then what we have introduction to constant optimization, like when we have some sort of limitations will be there or some constraint will be there, so that we have to see out, and then accordingly we can get the best optimum value and all. After that, what we were having that descent, gradient descent will be there, like a second derivative or like something that gradient of the gradient will be there. And then the proof will be there. So that proof that you can go through by your own. And then stopping criteria will be there, where to stop, how to stop, that all criteria that we'll see around. Then the packages will be there. Packages that I told like that MATLAB and all will be there. So shall we start for the today lecture? I think this is the number is enough. So we'll go ahead with the like we'll start like if someone want to join, then we'll let them enter into the. So anyone have the doubt till the second week, like third week today we'll discuss. Anyone have the doubt regarding the like third, like still second week? Like first week was the algebra, second week was the probability. In that we have seen expectation, variance, and standard deviations, and that all we have seen. Okay, so that hopefully no one will have the any doubt and all. If you have, so you can just please speak, or maybe you can put the message that I'll see around.
Good evening,
We'll
sir.
go with, yeah, please.
Yeah, sir, no doubt the sessions are very good, the problem solving sessions, and we are getting practice of how to solve the
Yeah, yeah,
things, actually, how to apply the mathematics into it. But
yeah,
it would be helpful if you can give some real time examples, any example. Like nowadays, we are using so many apps and AI is into our life.
yeah.
So no, I just understand. you can call me as a beginner, and since last 1 year, I'm just trying to study this machine learning.
Yeah, yeah.
And probably what I had encountered to calculate the performance metrics and all, the evaluation and metrics and all, we are applying the mathematics here.
Yeah, yeah.
But if you can give us, sir, some example, like, so that will be very helpful.
Yeah, sure. That will give it to you. Like we are in the starting phase for this course only. So once we'll get into that performance matrices, maybe we're going to start with that an end that's called neural data network. And in
Okay.
that also we can do the classification performance that we are doing with the what we can say confusion matrices, or maybe that what is accuracy, precision, and all. That we'll see how I'll show you that some sort of some data will be there, and that data I will labeled it, and will show you like how it will go and all.
Sure, sir. Thank you.
So
Thank you very much.
yeah, please have some patience, like at least for 1 or 2 weeks. Once we'll go that level, then we'll go. I'll show you like how the data. I'll show the data set also, and the data set conditions also, how we'll do, because this course will be having the agenda, like it's going to starting the course, also we have to be bit of familiar with the basics. Then once you start, that's the fourth week of the course. That's going to start with the linear regression, and in that only we are going to start with that on deep learning, or the new that is a neural, that's the network. Okay, so we'll start for this week. So if you talk about that, how a machine is going to store the number, because if we talk about if we see around, if you see around, like in the pen and paper, just one minute, or maybe that a traditional and all, they can have the infinite precision. And even we can show with the like 1, 2, 3, 4, 5, 6. It's up to whatever that maximum we have, that what we have. But the thing is that once it come to the machines, they'll be having the finite precision. Finite precision, like they have the certain limits will be there. If you see around that we have it, the 32-bit and 64-bit. 32-bit we are saying single precision. I think don't worry about this is all architecture of the machines and all. So I'm just saying like how the machines is going to store the numbers. So accordingly, when we are going to give the input, so we have to convert into the machine language. It's not about that we will give directly to them. They say like I am. This is a part of the computer science, and computer science. So they have to. We have to like that. The computer is actually going to replicate the what the human being wants to know or what to do, like wants them to do. So, but the thing is that what that computers or the machines have certain limitations. That limitations it likes they so they are not going to free forward to give any language, any sign language and all. They will give it that give it the answer. So they have the constraint. They can understand the only binary number. Binary number either zero or one. Like zero, like no, or maybe the one is yes. So that's how the things is working. So that's why whenever we are going to give, just 1 minute, I'll put the. Okay. So the thing is that like why we are going into the like architecture of that the machines, because when we are like so that we have to know that like a machine which language they're going to understand it. Because if we see in that our cultural and all, like say in the south there is Tamil, Telugu, Kannada and all will be there. And if we talk about if we talk about the North, Hindi, Gujarati, Rajasthani and all languages are there. So it's something that the human can adapt with that. But the thing is that, just 1 minute. So the thing is that so that the idea that why we want to know that what is the language of the machines and all, it's something that for a human being what they are going to do, like they can learn that's the multiple language. Even if they are familiar with the English, even they are familiar with the Hindi, even they are familiar with the those who are not convenient of their own languages. Let's say they can go with the if they're from North India, they came to the South India. Like as I am in the South India, so I am a bit familiar with the Tamil or maybe the and that is the other language also. But the thing is that for the machines, there is a constraint. They can get only the stored number, well, either the zero or either the one. So that's why computer usually uses the binary based system, either the zero, either the one. We'll go a bit slow and then we'll try to solve, because it's optimization that we all know that what is the purpose of the optimization is to find out the best value, either the maximum, either the minimum. And when we talk about the like accuracy and also we have to be maximize accuracy. But the thing is that we are trying to minimize the error, because we'll not talk about the something else. We'll talk about the minimizing the like our variability or the problems and all. Like Just see how the glitches are happening. Okay, fine. Okay, so before that, we'll see like if we talk about the how can we represent the number. Let's say if it is 1, 2, 3, 4, the same thing can be represented 1.234 into 10 to the power and like 4 or 3, is it? So we can do like this also. But the thing is still that is going to be but the thing is that for the machine it should be a base of 2, not the 10 to the power or 80 power something will be there. That should be not there. So that is very important whenever we are going to give. Can anyone tell like that my slides are okay or it's something getting stuck and all? If it is like this, so then I'll check with this. It's visible
Okay,
or
sir.
not? Okay,
Okay,
fine.
okay.
Huh. So if you see around, so that will be either 1, 0, 1, 0 or 1, 1. So either it can be 1, 0, 1, 0, it can understand. So what we have to do, we have to transform the real number into the binary, that is the binary system and all. So that is the purpose that we have to, first we have to, let's say I have trained participant. We have the untrained in there. So what I have to do, they have done the both exercises. Like let's say they have done the sprinting they have done. So now I want to classify. To classify, it's something that trained participant and untrained will tell they're not going to, that the machine will not understand what is the trained, what is the that is a untrained. So what they will do, like okay, for the untrained, we are going to label it as a 0. If it is going to fall category under the 0, so they're going to classify as a untrained. And if you talk about the trained participants, so we're going to label it as a 1. So this is how things, and then corresponding to the trained and untrained participant will give some features, or maybe we'll do some signal processing. We'll give the features, and then we'll ask the machines to learn. Let's say we will be having data sets, so that we have to do what we can say validation, like how the data set was divided, 70% test or 30% validations and all. So that's how it will go. So that's how we'll go and all. So that's why whenever any inputs or any numbers are there, so that we have to convert into the machine language. So that is the very first task to do whenever we are going to start any of the machine learning, that is a problem or maybe the models also. So that is the one thing that we came across that. So in that also floating point representation, like floating point is something that we'll be having, like a real number can be presented into the binary. How can we that, let's say it's a 5.5 is there. How can we do it? Can anyone tell? 4, 0 plus 1.5. We can do it. When the someone can ask the question like why can't we go for the 3 and all. So I'll tell you that is the why we're not able to go and all. Okay, so the thing is that I told you that machine language, they're going to understand the binary language, that is the binary language, and that too of the base of two. If it is 16, so we can go with the 16 something, or is 17. So we can go with the 16 plus 1, or maybe 0, 1. We can go ahead with it, or maybe 0, again 0, 1. Because the 2 to the power 4, 2 to the power 3. So it should come like this. It should, like that flow should go. So that's why we have to go with that is always the multiple of what we can say 2. It's something called the base 2. So that's why how I went. So because anyone just just 1 minute. Sorry for that. Something I don't know, but that my system is like behaving some different way. Okay, fine. So that some might have think like, okay, why can't we go for the two, like three or one and all that all? So that's what I told. Like when the machines they're going to store in the binary system, binary zero or one, and that too base will be two. If you see here, base will be always two. But if you see in the real time, what we have with that we can store into that e to the power something, 10 to the power something. Even the log also we can do. But the thing is that for the machines they can't understand that one. So that's why we have to go with like this one. So 2 to the power 0, or maybe like even go with the 1 into 2 to the power 0 into 2 to the power 1. And even we can go with the 1 into 2 to the power 0 and plus 1 into 2 to the power minus 1. So like it's something the inverse will come. So that's how it will go. 2 to the power 2. Sorry for that. So 1, how it will look like 0, 1, and then point will be there, then 1 will be there. So that's how they're going to store the number in the machines and all. So if we talk about like how it will go into that floating point format in general, it will go plus minus s into b to the power e. So that b s is the significant, like significant, or maybe that the you can say significant will be the e is actually a exponent. S is the significant. And if you talk about binary float number, that can be done with the plus minus 1 plus f into 2 to the power e. So this is the floating point in general. But if you talk about like binary one, so 1 plus f. F is the mantissa. Anyone know like what is mantissa actually? It's a if you have that study the fractions and all that you will get to know that what is that. And e is the, as usual that we know the exponent. Okay. So this is the how the numbers so this is the how the numbers will going to translate into the binary systems and all from the from the real number system to the like into the machine language will be there. So if you talk about like that standard for that like precisions and all, so we have what we have. If you talk about the IEEE standard will be there one. So it's a single precision. It's called 32-bit, and then we have the double precision. So I will not go much of detail of this that detailing and all. So I will just tell you to go and like the some books with architecture of the machines that you will get to know that. So even if you are aware of that the systems like a 32, that is a Windows 64-bit Windows and all. So that's how it's that the number they're going to so they're going to restore or maybe they store the numbers and all. So in the 64-bit that the number they can store it's like more than that's what they can do. The number storage capacity will more compared to the 32 bit, that is bit and all. So till now, what we have done, we have stored the number. But the thing is that what will happen in the real case, but what will happen in the real case, it's going to either underflow, overflow, or condition numbers. So a system will be having some sort of limitations to store the number also. a system will be that can have actually that limitations to store the number, either it's in terms of that the negative numbers or maybe the positive numbers and all. So in that also, that when the numbers will go up to like that the beyond of the limit, if it is going beyond of the maximum limits, that will say, oh, that will say overflow. If it is that going beyond of the something called that just if it is going beyond certain, beyond of the maximum, we'll say overflow, or it's going below of minimum, we'll say underflow. So if we define the underflow, that how underflow happens when the number approaches toward the zero. So when the number approaches toward the zero, or it's going to being round off toward zero. So what's happening? Let's say this is the case of one. Okay. So maximum behaving very weirdly. Okay, so what we have, let's say this is the one positive side, negative side. What you can say, maximum positive number. This side will be the negative, maximum negative. Maximum negative is something that's going toward the zero, minus infinity, and all that that we can say. So if it is going beyond of this limit, so it will tell overflow. If it is going beyond of this positive maximum also, that will tell overflow. Okay. If it is coming under this range, so we'll say underflow. If we talk about that our system that will be having something called like that the maximum case of 1024, like that e to the power 1024 only. That's the maximum that that system can go. If you took e to the power minus 308, like 1024 is the limit. If you go to 2, 2, 2, 2, so it can go e to the power minus 308 or to the power plus 308. So if it is going beyond of this, so it's an underflow. If it is going like that's so that's going to be more of this. So it will say overflow. Okay. So that's how that the concept of the underflow and overflow came. So whenever we are going to define a number or maybe the variable or maybe the data set size and all, so that we have to be careful, like how much or what is the system capacity, that we all know that it can go up to the case of 1024. And so if it is the power that we are going to enter, so that we have to be that little bit careful that what are the that the number of input that we are giving and all. It's a power, not like exact 1 to 4. Because if you see the number like e to the power minus something will come into the pictures and all, that will go beyond of much that is smaller, or maybe that it can go much of larger also. So can anyone tell what is the conditions number? Conditions number. Conditions number. If I'll say that conditions number is something. Just 1 minute. So conditions numbers like something that is going to be if it is going to ratio of that any of the value, like if it is going more than that of one and one, so it's what, like it's going to ill conditions number, like it's not stable. If the variabilities are more or less, so if the variabilities are too much, so what will happen, it's going to be a like conditions number, ill conditions numbers and all that we are going to. So limited percent. Okay. So what will happen, like if it is going to be like 0.9999, but if you see sometime in that it will go 0.99965754. So what will happen, that's going to that the precision is going to propagate, like it will change, like it will, things will go, and so that's why, so that we can't go beyond of certain data precisions also. So in that case, the number is going to be like ill conditions and all will be there. So what is that? In general, conditions of A will be that the norm of A and norm of A inverse. If it is this value close to 1, it means stable. If it is going greater than of 1, we'll say unstable. It's a, or we'll say ill conditioned. So that we'll see some examples of this also, like when it will come, when I will going to introduce the MATLAB packages, or before that I'll see like how that so that the MATLAB will show ill conditions numbers and all if it is not properly like defined and all. So that's how this is called the machine languages. So that's how. So we have to know like how we have to give the input to the like to the machine. So simply a image is there that we have to, now we have to classify the image. Let's say if you see for the that is that for the car and all, that based upon that images and all, they're going to say, okay, this is the things that like traffic is there, or maybe if you see the Tesla car and all, so they will do classify and all. So in that machine learning, so we simply can't feed the images, we have to convert into the that is RGB, that category, or maybe that number, and then we have that will give the input to that's the model, and then they're going to classify and all. Then it will going to work it out. Okay, so this is how we have to convert to the that's called machine languages. So now once we have done with that, so now we have to go with the optimization. So the first thing will be having the derivatives. Why do we need to talk about, or why do we need to study about the that is optimization? Can anyone tell? So if we talk about the derivative, that is the usually we'll speak about in the scalar and all, and that we have already studied in our 12th class or 11th class and all. So derivative measures how much one quantity will change when there is a small change in the another. That's how the things will go and all. So when we're going to change one, let's say y is equal to fx. So dy by dx, like it's a change of like dfx by df by dx. So if we're going to change in the x, so then how it's going to vary in the f, or maybe the y. So that's how the things will go and work and all. So it's going to give the slope of the tangent, like it will give the more data slope of the tangent. So if you talk about the f of dash a, It's a dfx limit of h tends to 0, f of x plus h minus f of x by h. So this is the how things will work out and all. So that's why this is the things will come into the picture. That's going to a single scalar, single valued scalar, single valued scalar and all. So the next one is that what we have like gradient. Can anyone tell like if you see in that machine learning, in the machine learning what will be there? We have that will be having the vector, not the scalar and all. That we have to deal about the. So that the gradient is the multivariate generalization of the that is derivatives only. Okay. So it is the vector component each directions. So how it going to be? So delta f of x1, f of x2 till xn. It's going to show in terms of del of f of x1, fx2 till it will go del of f of x2. It's a vector. Can be used for what? Like it can be used for just 1 minute. It can used for so we can use for the finding out the direction of the partial derivative also. This is the one parameter. So for that look that like that the derivative is actually for a scalar, and gradient is for actually for vector and all. So now the third term what we have is the Hessian. Hessian, anyone like that heard before? Hessian actually it's called gradient of the gradient, gradient of the gradient, and it is actually equivalent of the second derivative in the scalar calculus, and the similar rules are there. So how it will going to look like? It's going to look like for f, it's the real number. What we have, we can get hij Hessian delta of f x I delta of xj. I think that is that you might have heard about the second order derivative, like second order partial derivative, second order partial derivative, and it will be always will be having n by n matrices, like it's a square matrix. So how it will look like? Hij is equal to delta f by delta. x1 x1 delta f delta 2 is similarly it can go delta f by delta xn delta x1 del, like delta square f by delta xn delta x2 and this is how it will look like the Hessian. So actually Hessian is going to be a symmetric matrix always. Always will be the symmetric matrix will be there. So now we'll come to the next part, like that will be called Jacobian. Jacobian is that is the equivalent of the gradient for the vector valued functions and all. Okay, so like it's a Jacobian of the gradient or G can be like. So how it will look like Jacobian delta x of f. It can be that a square matrix or like its size of the m by n. But that the Hessian will be the always the square matrix will be there. Similar way we can go with that. Till now it can go m by n matrices and all. Okay, so Hessian can be seen as a gradient of the gradient and all. So can any like Taylor series actually is a local approximation of a function value in terms of the polynomial, and that is going to use in that multiple field also. Even we are seeing in that our derivatives also, and that numerical methods also, and even we are seeing in the some other example fluid mechanics and all that all we can see around. So if you see that in general, f of x is equal to f of x at the 0 plus x minus x at 0 dff by dx like del plus 1 by 2 x minus x naught whole square delta f by delta x square. So and so on will be that will go. So if we talk about in terms of what you can say vector, so we'll go with the either like f of x. This is for scalar, and the vector can go f of x is equal to f of x at 0 plus x minus x bar transpose gradient plus x minus x bar 1 by 2 transpose Hessian of at x minus x bar and so on. So this is terms will be the gradient and this terms will be the Hessian. And that the higher order will not go with that because it will become the more complex will become. So till now that we have seen that is the very simple part like derivative and then the gradient, then the Hessian, then the Jacobian. That how can we get the derivatives of that? Now now the things will start like how we can get the optimization value and all. So why do we need like for the optimization for the machine learning and all? So if we talk about the basic idea behind it's going to be a machine learning to build the model that going to map input data to the output data. So for the mapping also we need the best value, best parameter. So that our that the so that the variability will be less and that accuracy should be high, stability should be high for that model and all. So what we're doing for that, we are going to drive the parameters of this model based on the training on some given data. Let's say we were having 100% data is there, data set is there. So we'll divide it into 70% training and then test 30%, or we are following the rule of 80-20 also. 80% of the training, then 20% of the test will be there. So that's how we are going to get the best optimum value also. Subtime, what we'll do, we are going to do the hyperparameter optimization. That all we'll see. Don't worry. Once we'll go into the our exact model and all, so so that will see that is that for the neural network, what will be that number of neurons will be there that is optimized, whether that the connected layer should be 2 or 3, or the hidden layer that is how much should be there and all. So whole of the machine as a process that find the best or optimal model for a given data. Okay, so that is that. Like if we talk about the machine learning, it's actually a optimization problem. Ultimately, it's going to be a optimization problems will be there. Okay, so that let's say if of x is equal to x1 square plus x2 square plus x3 square. So how can we get the optimum value where it's going to find out? So that's the thing that we have to find out. And the function, that function will tell what objective function, or the cost function, or the loss function. Okay. So if we talk about in general, so general task, optimization task is to minimize or maximize a function by varying the x. So optimization is something that we are going to either in the optimistic way, optimistic like it's going to be a positive or it should be going to negative. Let's say positive, I'll be saying so for a like that the healthcare that the our accuracy should be low. If you go with the negative, like said that the variability should be less. Variability should be less, like it should be that the error should be less and all. Okay, so that function actually it's called which function that function actually called objective function, cost function, or the loss function we can say. The function scalar that can be of single objective, or a vector it can be of multi-objective. So for this ML course and all that we're going to mostly with the scalar, like that function, cost function will be the scalar only, but the vector will be not there. So that fx will be the that is a scalar, but not the like whole model will be the scalar and all. So in a general, what we'll say that f is going to belong real number into real number, that's the natural number. Okay. So the thing is that in the whole of machine learning, that we are going to find out the minimization problem. So means loss should be, even though the functions will be that we're going to maximize, so we are going to put minus of fx, it will turn out to be the minimization problems and all will be there. Okay, so any problem that can be fit into the minimization problem, let's say fx it came maximum. Same thing if you are going to convert into the minus of fx, it will turn into the minimization problem. Maybe it will be a bit of boring, but I'll go like to solve the problems and all now. So let's say if going to f of x is equal to fx x square 1. So min of f x will become 1 for x is equal to 0. So similarly, that optimization will be the scalar. See that. So that is the why I am saying that become the scalar and all for a given model. the parameter or that best data will be the only one. So that will be the x, or maybe that's going to be a scalar only. For a single model, that can't be the different parameters or different optimization forms and all. So that's why we have to think about like that our objective function will be the mostly it will be a scalar, but the whole model will be the vector because we have to deal with the data with the into the vectors and all, but not the cost function or objective functions and all. So for a one objective function, one best parameter will be there. So that's why so we have to think about that one also. So now we'll go with that. Now we have done with what you can say. What they're going to do to find out either the local maxima or the global minima, global maximum, or the local minima and all. So how can we get it? Any idea and all that will be there. So if you have that heard about that, to get the DF going to derivative that should must be equal to 0. Now to get whether it's a maximum or minimum, we have to get another derivative to see what is the nature of the value based upon that going to be we are going to decide and all. So through that we can get the that's called local minimum or maybe the local maximum or saddle point. So before jumping into the how to get the local minimum, local maximum and saddle point, we have the two types of the optimization problem will come across. Can anyone tell what will be there? What will be the constrained, unconstrained? Second will be the constrained optimization problem. Okay. So can anyone tell like what will be the constrained ones? How it will look like? Constrained.
You will be having the range of the data, some
For the
conditions, some bounds.
unconstrained, there will be no limit of the x. Like we have to get the best optimal value in the whole, that from the minus infinity to plus infinity. Is it? Maybe that fx that minimized with the x belong to real number. So, but there will no limit. If we talk about the constant, so it can be stored. I'll take one page extra actually. Oh, one constant will be there will be a If x belong to R, real number. It means whole real number line. So it can be like how can we go? So we have to find out the properties so that local maxima or minima at f dash x is equal to 0. So such point, like this point, we'll call a stationary point or critical point. How we'll get it? Like how we'll get it? So if f of double x or double derivative will come greater than, it's a local minima. If f of double x will become negative, it's a local maximum. If second derivative will become equal to 0, it's a saddle point. Okay. So now we'll go with the this is the singular one. Fx is equal to. But the thing is that in the machine learning, we have the multiple variable. So now we'll what will go? We'll go with the multivariate of x, like x1, x2. So since x is going to be a multivariate, earlier it was the x is the like x was scalar, but now is the x is the vector. So we have to find out the partial derivative. Okay. So it can be shown like we can get the either maxima or minima at del x f is equal to 0. Either it can go delta f by delta x is equal to 0, delta f by delta x2 is equal to 0, or delta f by x3 is equal to 0. Okay, so in that case, like what we get, so that point can be any point, stationary or like that can be of local maximum, local minimum, and all will be there. So types of the critical point. So types of we can get through the how we can get through the by the nature of the Hessian. In the case of scalar, we went through the double derivative, but in the case of vector, what we have, we'll be having a Hessian. So Hessian, what is that? H I j is equal to delta square f delta xi delta xj. If Hij is going to be if Hij is going to be a positive definite, so we'll say local minimum. If Hij is going to be a negative definite, this one we have seen positive definite and all that in the last class. It's a local maximum. If Hij is going to be a 0, indefinite or zero. Means like one x is the positive, x1 is the positive, x2 is the negative, or x1 is equal to x2 is equal to 0. So we'll say saddle point. Single point we'll say. So now we'll come to the constraint optimizations. So if you see earlier what we have seen, we have to seen what we have seen like it's a something we have taken one functions and all. Now we will be having that functions will be directly will be there. So a general constraint optimization task is to maximize or minimize a function by varying x given a certain constraint on x. Constraint like earlier till now what we have seen only till unconstraint. It's a x belongs to real number. Okay. If you see about what is that examples and all, so designing the fastest vehicle with the constraint or on the fuel efficiency. Let's say that if that automobile company and all that, so they are going to design the car and when the power is going to increase, so what will happen so that that our fuel efficiency is going to down or maybe the cost will increase. It's something that we have the constraint will be there, or we are saying find the minimum value of this for all the norms that should be greater than of one. So this is how the things will go into the picture, like how it will look like and all. So that's why most of the ML problems and all that will go and deal with the constraint only. Like we'll give them some input and then we'll ask them to classify this between this to this only and all. And then, but the people are like now they are doing with the transfer learning and maybe that functional learning and all, so that they are dealing with the that unconstrained or constraint problem also that they're dealing with that. So if it is we have two types of the constraint will be there. One is the equality constant. Constraint. It's something x1 plus x2 plus x3 is equal to 1. Like summation of the all x will be like it's going to equal to 1. The second one is that minimize of the fx, fx1, fx2, fx3, that one function is there subjected to that the summation of their all the points should be that's going to be all less than of that one. So that's why in the constraint will be either will be having two types of the equality will be there. Two types of the constraint will be there. One can be so in the constraint we have seen and unconstraint we have seen. So now one more we have what we have it's called the Lagrange equations. Lagrange equations is actually requires us to minimize the function that the vector while ensuring that the point discovered belong to the feasible set. Feasible sets is something that we will be having the data set will be there. Like we are going to this is going to be called okay. So it's going to be like we are going to generalize or we have to keep that our functions in terms of this is going to be a, like something called vector. This is will tell like equality constraint. So then constraint minimum minimum of f of x is equal to minimum x lambda alpha. It will be the x lambda alpha. Equality in equality, so it's something like directly we'll get directly in terms of like how we're getting known. So now we'll come to the numerical optimization problems now. Can anyone tell like, what is the purpose to get like numerical optimization problems and all? To optimization like that we have seen as far as the and that is the analytical. But the thing is that we have to, whatever the objective function is there, we have to explicit that expression that we need. With that needs some across the, we need some functions or maybe that expression to express that our objective functions. Because the thing is that what we'll be having, it's a black box, like it's called machine learning model. Input we have given, output we have given. So in that case, like what we have to do, like we have to find out like how the things will go. So that should be like our the things will be, we have to express the features in terms of some sort of equations, and then we have to solve the numericals. That like it that we should solve the numerical. Let's say what we have the examples of j is equal to omega 1 square plus omega 2 square is equal to 4. So what will be the gradient function of this? Be del of j omega 1, it's going to be a 2 omega 1. Del of j into omega 2 is equal to omega 2. So gradient vector will become how? 2 omega 1 to 2 omega 2. So now the thing is that what we have to find out? Gradient descent. Gradient descent that we have seen across, like it's the gradient of the gradient that we call gradient descent. So if we came across, so we have to find out what we have to do. We have to find out the gradient descent. Something like we'll tell omega of new at what? Omega of old into alpha of gradient. Alpha is actually a learning rate. If it is too big, oscillation will happen. We'll solve some problem or not, that will tell you. If it is too small, if it is too small, it's going to like slow learning. So what we have to do? We have to find out the we have to find out the word. We have to find out the word like we have to find out the minimum at 0, 0. What will be the value of omega 1 and omega 2? So we can start with the omega is equal to 3 by 3. Omega 1 3 3 3. But they are saying to find out the minimum at 1. So it will go iterative process. I have one code actually. I'll just explain to you like how the things is going. Thing is that we have to start at the omega 1 and omega as a, like what you can say, 3 and 3. Then we have to go with the omega that is new. Then omega old will be there. Then that's the gradient will be there. 2 omega 1 to omega 2. Just 1 minute. Again, got stuck. Just let's see what we have. We'll be having that that is a quad function. That is omega 1 plus omega 1 square plus omega 2 square plus 4. Gradient function that will be that what will 2 omega 1 to omega 2. Then we are going to define a line like linear space minus 4 to 4. And then we're going to that alpha is the maximum that is that learning rate. And we want to go till that is a iteration 25. And we started with the how much? We are starting with the 3 and 3 that I told earlier also. So what they will do, like they're going to path 0, then 2, and then it's going to maximum iteration. So if you see that how it will look like. This is how earlier it was the point at 3, 3, 3. Here, somewhere point was there. Then it came here, then came here, then came here, then slowly came here, slowly came here. So it's something like it's going from here to here, like it's the we are going till close to what we can say that the we can get the value at the 0.00. So this is how the things will look like and all. So this is the contour for the JD path, like JD path means the gradient descent path and all we can see around here. If we change our that learning rate, so just see that how the shapes got changed. Path will be same. Always the path is same. But the thing is that like that the learning rate is going far. If it is point 0.2 or point 0.3, just see how it's look like. That the value got changed here. So this is how things will work out, and then we have to see it around and all. So now we'll go. The question will be there where to stop and how to stop. Whether because in the real time, what will be there? In the real time that we can't go till the 0. If we talk about the ideally, so that should be gradient descent should be equal to 0, or maybe that the gradient should be 0. But it's going to not happen in the real life and all. So what we have to do? We have to define one epsilon. Epsilon is called error. Let's say I'm going to decide like a 10 to the power minus 3 or something more of that. So in that case, so we have to follow omega k plus 1, like that is the new one, minus of omega of k, then the norms, it should be less than that of. If it is going beyond that, we have to stop it. Or maybe that gradient itself, it should come below of epsilon only. And one more thing is that Jacobian, like that's the gradient itself or Jacobian itself, you can find out j of omega k plus 1 minus j of omega k plus into minus of 1. So this is the thing that we have to follow it up, like when to stop and how the things will go and find out. So based upon the what we have done, gradient descent, derivative, Jacobian, and all, we'll solve some problems So let's see how it's going. So okay, like that before going into the jumping to the what we can say solve the problem that we have the some MATLAB packages will be there. MATLAB packages that actually that what we have is that one is that image processing and computer vision. Second one will be that that's called that the machine learning and that the deep learning. Like it's going to complement with the statistical toolbox that we have to figure it out and all because when we what we have got to do yeah, one minute. So a statistical toolbox will be there, so that that we will do around on. Even but is there if you are comfortable with the writing the code, so that you can write the code and then we can play with the things. If you're not comfortable with writing code, there's a like package will be there that we can give the only that like state of the architecture will be that already defined and all. So we can just give the neuron number of hidden layer or even for the SVM also that parameter we can give it on that we can get directly the results that that we don't need to write the explicit code for the our problems and all. So that we'll see in that both cases. We'll solve the packages also, and I'll show the some codes also that how that we can play with the our parameters and all. Because sometimes that we'll not able to play with the like a parameter in the package and all. So can anyone tell? This is the first question that we are going to see. First question is that while training a machine learning model using gradient descent, you observe that the cost oscillate up, down without clear conventional drivers. Which of the following adjustment is to learn that the learning rate is most appropriate? Appropriate. Can anyone tell? We're saying like we observe that cost oscillates means that the learning rate was high. So we have what we have to do? Anyone know the fund of this? I'll just tell the answer of this. Like what is the answer of it? Is that is the ready with the answer? No, no. Okay, I'll tell the answer.
Hello, sir. Can I try?
Yeah, sure.
Actually, as per I may be wrong,
Yeah.
as the cost oscillation is oscillating from up and down. But sir,
Yeah.
it is mentioned that it is not converging.
Like it's not going to clear convergence or not divergence. It means that
Yeah, yeah.
what we have that the alpha is supposed to be high, means high.
Okay.
Okay. For the
Huh.
adjustment to get the stable, we have to decrease the like
The load.
something called learning rate. Is it?
Okay. But since it is oscillating,
Yeah.
can we just keep it unchanged or slight change, or we have to change it, sir? I am
When
doubting because it is mentioned that it is clearly not converging or diverging.
yeah.
So
So
it
it
may oscillate again, sir. So no, I am just having the doubt actually.
yeah, yeah. Actually, the thing is that like I'll tell like it will going to it is going to oscillate like it's going that it's getting the oscillation. It means they're not getting the convergence also. Just a minute. That means it's not getting convergence also, and it's getting what's happening. It's getting up and down. So there is a instability is there. Instability is there means that our alpha. It means that the learning rate is like slightly high. Means they are not able to catch up the things. So it's getting up and down with there. So for the better stability or maybe the adjustment need to be done so that so that we have to decrease the learning rate. Just see,
Okay.
like it it getting closer to the convergence. It getting too much divergence also. It means like that the model is getting failed. But the thing is that it's getting up and down. So it means that the learning rate is not appropriate or it's too high. It's not able to catch the whole segment of the data and all. So that's why we have to keep the learning rate a bit of low so that it will become the process will become slow so that they will be able to read that or each data set and all. Then it will going to converge. Like it's going to map the input to the output. Is it clear?
Yeah, yes, sir. Yeah, thank you.
So that option B is the correct option actually. So now we'll go with the one that the numerical problem. So to reduce the oscillation, oscillation is actually it's going to high learning rate. For the most appropriate, we have to decrease the learning rate. So now that we have the one question is there that's called cost function is there. Is given j is equal to 3 omega 1 square plus 2 omega square minus 12 that's omega 1 plus 10 omega 2 plus 15. So they are saying to find out the critical point of the functions. I'll just wait for the 2, 4, 5 minutes, then that you can do it. Like you can give it. Like what is the that's option for the critical point. So if you see that given equations that we have given, it's called cost function actually. So anyone is ready with the answer? Just tell me. What we'll do to find the critical point? We're going to take the derivative with respect to the each like variable. and we're going to equate to the 0. What will look like? 3 omega 1 square, it's going to be 6 omega 1 minus, this is going to be plus 0 because it's not that, it becomes the constant with respect to the omega 1 minus 12 omega 1 like will become the 1 plus again it becomes the constant for them plus 0 is equal to 0. So 6 omega 1 is equal to 12. So omega 1 it will become 2. So that is the, so this option is going to eliminate. So now for the second one, what will be there? Delta J by omega 2 is equal to 0. So what is there? If we take for with respect to the omega 2, omega 1 will become the constant 0 plus 2 into 2 into 4 omega 2 minus this will become 0 plus 10 plus 0 is equal to 0. 4 omega 2 plus 10 is equal to 0. So omega 2 will become minus 5 by 2. So option C is the correct, is it? So option C will be the correct. Shall I go to the next question? Shall I go? So what we have the same functions what we have. So they are saying I want to find out the critical point identified in the question 2. Like now the omega 1 we know that 2 and omega 2 we know that minus of 5 by 2. So they are saying to find out the critical point. How will how will get it? Get
Second derivative.
yeah, second derivative. We have to get the Hessian. Hessian is second derivative itself. So h is equal to, so it's going to look like what? 3 into 6, then all will become 0. 0 because we don't have the combined omega 1 and omega 2. For this also will become 0. Now this also will become 4. So if we can see here, what is that? Like it's going to be a like the positive and determinant of H also it's a positive. It's a positive only. So it's a positive definite. Positive definite means local limit. Okay. So that option A will be the correct. I think it's clear now. Now we'll go to the third question. No, fourth question. Same function is given. So for the given functions, assume that we are going to start the descent from 0, 0 with the learning rate of alpha is equal to 0.1. They are saying compute the value of omega 1 and omega 2 after the three iteration of the gradient descent. So it's a bit lengthy process. We'll go slowly. We'll do it. Can anyone tell what is the first step? We all know that like alpha is given and starting point also given. Okay. For gradient descent, what you have to do? Updation rule. Omega t plus 1 is equal to omega t minus alpha gradient descent of j of omega t or omega t at the top. Okay. So how will get it? So gradient, how will you find out? Is it? This is the gradient vector. So now we'll go with the iteration one, where 0 and 0. Omega 1 at 1 will look like what? Can anyone tell what it will look like? 0 minus alpha is the point 1. And if we keep the value 6 omega 1 and all, so it will become like your minus 12 is equal to 1.2. Omega 2 will become 0 minus 1.1 into minus of minus 10. Like, like sorry, it's a positive only now. So it became minus 1. So what the value for that iteration second? What we have? 1.2 and minus 1. So now we'll go with the second iteration. 1.2 minus 0.01 into what is that? 6 into 6 into 1.2 minus how much will come? 12. What is the value? 1.2 minus 0.1, it will become 0.48 because 4.8 12. 4.8 12 like become like how much? 4.8, sorry. So it will come how much? 1.68. So what will be the omega 2 at second iteration? What is the value? Minus 1 minus zero point 0.1 for omega 2. Omega 2, how much was there before? How much was there? Minus 1. Minus of plus of 10. So if we calculate that, we got the value of how much? 1.6. Okay, so we got after two factorization value is that after two iteration we have the value of around 1.68 minus 1.6. We take one more extra page and we'll do it. Okay, so what was the value after second iteration? Now we'll do 0.1 6 omega 1 6 into 1.68 minus 12. If you can calculate, the value will come how much? 1.872. If you calculate the omega at 3, minus of 1.6 minus 0.1, 4 into 1.6, that should be minus 9 plus of 10. So if you calculate, it came around minus of 1.96. So the final answer is that 1.872 into minus of 1.96. So that the option will be D is the correct. Okay. So now what we have, the fifth question. What they're saying, we have to find out, consider the cost function the same. For the same function given above, assume that the start gradient was at the 0. But the learning rate, earlier it was a 0.1, now it become 0.2. Find the value of omega 1 and omega 2 after the 3 iteration of gradient. Which learning rate brings the point closer to the theoretical minimum of the functions? Can anyone tell how it will look like? So we have to follow the same procedure. So we got for alpha is equal to zero point 0.1. We got how much? 1.872 minus of 1.96. We got it. We got it. So now we have to get for the alpha is equal to zero point 0.2. Everything will be same. The thing is that we have to start from the 0 0. The way we have started here. The way we started here, 0 0. So that the value will be, it will change. How it will change? Because it's a that alpha is going to change. Earlier it was the zero point 0.1, now it become 0.2. Can you someone tell the value of omega 1 at the omega? And which, so same procedure that we need to follow. Omega 1 is equal to at 0.2 minus of 12 is will come 0.24, 2.4 to 0 minus 0.2 into of 10, it will become minus 2. So now we got omega 1 as a 2.4, 2.4 and 2. Okay. So now we have to get the omega 2 at omega 1, 2. So what is the value? 2.4 minus of zero point 0.2. We have to put all the value. So in that case, what will happen? So it's going to uh, 0.2. So I'll show the MATLAB code. So when when that alpha learning rate was there, that one. So final minimum point was there how much? Just I'll show to you. Final minimum point is 0.0013, and or it's there. It here actually iteration I'll go by 3. I'll go with the 0 starting point, 0. Now we'll see how it look like. Because why it's coming? Because you show into the that is a like decimal point we have to see, because that we have kept only 2 only, so it's not showing. Find like format long enough for for that format like code and all. So what will happen then if we change with the 2 also? only because it's become very. Let's see from this later part. So actually, point two will become what will happen. It will become the move the point faster toward the minimum. So if you go and solve this problem, that's how how it's solved that I have explained. Now you can go and solve this problem and all. Now what we have one more question that we have. Now earlier what was that we were having only one data set. Now we have the set of data set is there x1, x2, x3. Then the cost function is there. So they are saying that theta at zero are initialized alpha is equal to 0.1. So they are saying after first iteration of the gradient descent, what are the value of the theta? What is the steps to follow that? Can anyone tell? One, one, two, 7. 2, 1, 3, 10. 3, 2, 1, 12. 4, 3, 2, 20. And Jacobian of like the cost function is given 1 by 2m. Theta naught plus theta 1 x1 plus theta 2 x2. So what will become? That will become h theta. Okay, so that we can write it like how that's how we can write it. Can anyone tell like how we can write it? Let's say that h theta will become theta 1. So gradient will become. So if you see the delta j by delta theta, so it's a square. So 1 by m summation of I is equal to m h theta into xi minus of yi into of x xj. You know. Okay. So at the starting, it's equal to theta is equal to 0. So h theta x will become 0. So that the error will become h theta minus y is equal to minus of y of 0 minus y. So we'll take one more page and we'll solve. Okay. So delta j, that theta will become 1 by 4 minus 7 minus 10 minus 12 minus of 20. So it will become 12.25. Delta J of theta 1. 1 by 4 minus 7 into 1, because we have the x value of the 1. Because here all x1, x2, x3, it was the x was a 0. So what are the value came? So x theta minus 0, like it will just now it will become 1 1 2 2 1 3 3 2 1 4 3 2 minus of 10 into 2 minus of 12 into 3 minus of 20 into 4. It will become how much? 7 10 into 2 12 into 3 20 into 4 35.75. So delta J by theta 2 1 by 4 minus of 7. What is the value of x? 1 1 2 3 1 2 3 4 1 1 2 3 1 1 2 3 2 3. It came around minus of 25.35. 1 by 4 minus of 7. What is the last one? 2 3 1 2. Now we have to keep the value of theta at 1. Theta 0. That we have to find out. Because so that the starting step is the 0 0 0 0. So that in the all cases 0 minus 0.1 of 12.25. Then theta 1 at 1 0.0.1 35.35. So if we solve all this, so we'll get the value of 1.225. If we solve all this, we'll get just 1 minute. We'll get the value of 1.225, 3.537. So that the answer will be for this A. Okay. So that the next question what they are giving. Hopefully this is so that the same step that what we have followed in the previous question also. The only difference was here. It's a cost function was different, and then data set was different. Data set was there. Earlier the data set was not like given, but now the as a, that what you can say in the case of what you can say that the linear equations that terms they are so they have given and all. So that you have to follow like this. And similarly, the second step also they have asked. Third step they have also asked. I'll show you the questions also. So what they're saying for the same data set, function as above, the cost value after the first iteration, what will be there. So how we can proceed with that cost function? So that we all know that how it came. Theta is equal to 1.225, 3.575, and 2.525, and to 4 came. So that we all know that like how it came. Computing iteration that came around h theta x at 1. H we know that theta 1 0, theta 1 x1, theta 2 x2 plus theta 3 x3. We can calculate now. Even we know the gem like we can. I'm trying to calculate this one at first for all the four value. For all the four value, then we'll going to keep the y value 7, 10, 12, 20. Then we'll get the cost function directly. So what will the x for the x1 at the theta 1? It will be there 1.225 plus theta 1. What is that? 3.575 into how much is there x1 for that particular case? 1 plus 525 into 1 plus 2.4 into 2. We'll get some value. Similarly, we can get theta of x at 2. So this all three we can keep it here. We'll get some value. H theta x3 will get some value. So that value is actually 12.125 and this is 20.1. H theta x 4 will get value of around 28.675. So now the cost function will become j is equal to 1 by 2m. M, how many are there? Data set 4. 2 into 4. So this for the first case, how much came? First one was the 12.125. Second one was the this is 1, 2, 3, 4. We'll get somewhere 28.675. So we'll keep all this value minus of 7, minus of 10, 12.175 minus 7 to the whole square plus 20.1 minus 10 to the whole square plus 19.925. So let's calculate on and all this will get around 26.137. So this is the simple that so that is simple one. It's the extension of the all column that we can see it around. Okay. So now the thing is that after two iteration, what will the value? Similar the same step. We can follow that what we have followed the earlier case and all. So for that, the answer will be somewhere around 551. Like how it will come that also we have some answer for this. It will come the A option will be there. So that we have to follow the same step that theta 2 will become theta 1 minus alpha and j delta of j. So that will be like the j function like gradient of j gradient not gradient of j. And after that, they are saying again to find out the cost value of the function. Similar like what we have done for the this problems and also. Okay, so this is the last question actually. What is the purpose of the generalized Lagrange equations in the constraint optimization? Can anyone tell? To maximize the number of constraints in the optimization problems? No. They try to minimize the optimization function, like that minimize the problem and all. And actually, they are doing what they're doing. They're doing to transform a constraint optimization into a unconstrained one by incorporating constraint into the objective. What we have done, fx That's the vector we have. Then equality constant, then plus inequality constant. Okay, so this is the answer. To calculate the exact value of the function, no, they're not going to do. They're going to just either simplify the problem and all. To eliminate the need of any constant in the function, no, they are going to actually add on to get the like optimum form, like to get the maximum or minimum. So second option is the correct option actually. So I think with this we are going to end the today's session. If you have any doubt in this, and I would like bit of sorry because my system behaved very differently today. So I'll try to rectify and then we'll see in the next class. If you have any doubt, please ask. Thank you everyone for joining the session. Hopefully we'll see in the coming classes that will be good enough.